Heterocyclic system. In this chapter, we are going to discuss about the heterocyclic compounds and the nomenclature of heterocyclic compounds. First of all, organic chemistry is the chemistry of carbon compounds. On the basis of carbon skeleton, organic compounds are classified into two categories. The first one is open chain compounds, which are further divided into unbranched chain, for example, N-butane C4H10, and the branched chain, for example, 2-methyl propane. On the other hand, the second category is closed chain or cyclic compounds. In closed chain cyclic compounds, there are further two types: homocyclic, for example, benzene, cyclohexane, and the heterocyclic ones, for example, furan and pyridine. Heterocyclic compounds, they're containing heteroatoms. Heterocyclic compounds are those which possesses a cyclic or ring structure with at least two different kinds of atoms, including the carbon atom in the ring. These atoms are also known as heteroatoms, and the most common heteroatoms present are nitrogen, oxygen, and sulfur. The heterocyclic ring, they may be fused, for example, which is given in structure first, or it can be bridged with homocyclic or heterocyclic rings. These heterocyclic compounds can be aliphatic or can be aromatic in character. Next is the classification of heterocyclic compounds. The heterocyclic compounds can be classified on the basis of nature or number of heteroatom present. For example, azoles containing nitrogen or thiophenes containing sulfur. It can be divided into or classified on the basis of degree of saturation. It can be aromatic or non-aromatic. It can be saturated or unsaturated. Next, the size of heterocyclic compound. That means the number of atoms making up the ring system, whether it is 3-membered ring, 4-membered ring, 5-membered ring, and so on. It can also be categorized into simple heterocycles and the fused ring system. Fused ring system are the compounds which are containing more than one ring. Now we're going to discuss about the nomenclature of heterocyclic compounds. There are generally four rules, the four basic rules for naming the heterocyclic compounds. The first one is the heteroatom is given a name and is used as a prefix. For example, nitrogen is used as Aza, oxygen is named as Oxa, sulfur, Thia, phosphor, it is for phosphorus, As, arsenic, Arsa, silicon, Silla, selenium, Selena, and boranium, Bora, and so on. The A ending is dropped if the next syllable starts with the vowel. Thus, Aza, Irin. It is an example. If your syllable starts with a vowel, that is A, E, I, O, U. For example, Irin, it starts with I. Then the A of the prefix, it is dropped. That means Aza, Irin, it becomes azarin. Second rule, ring size is designated by stem that follows the prefix. For example, 3. If your ring is 3-membered, then you'll use the prefix er. If it is 4-membered, et, 5-membered, ol, 6-membered, in, 7-membered, ep, 8-membered, off, 9-membered, on, and so on. Third, if fully unsaturated, the name is concluded with a suffix. For ring size, fully unsaturated means it is having double or triple bonds. Like for 3 atoms, it stands for ene. 4, 5, 6 atoms, there'll be no E. There'll be, except nitrogen, there'll be ine, and for 4, 5, and 6 atoms, there'll be no E. For 7, 8, and 9 atoms, there will be ine. The suffix will differ on the behalf of your number of rings, atoms. If next fourth rule is if fully saturated, the suffix is ane for all the ring sizes, except for nitrogen, which uses iden for rings of 3, 4, and 5 atoms, and for 6 atoms, there is a prefix of hexahydro. Also, the name oxane, notoxynane, is used for six-membered ring with O present. Other exceptions also exist for compounds like phosphorus, arsenic, boronium rings, but they are beyond our scope. The rules I've explained, they can be very clear with this table since it contains the size of ring. For example, it is 3, 4, 5, 6, 7, 8, 9 and 10 membered ring. Next row is for rings containing nitrogen. Further, the rings containing nitrogen can be unsaturated and can be saturated. Unsaturated means they're having double or triple bond. And the saturated means they're not having any sort of bond. If there is three-membered ring and it contains bond, means that is unsaturated, you will use the suffix "-eren". And if it is saturated, then it is "-iriden". Similarly, for the four-membered unsaturated, 8 and saturated "-etidine", 5 unsaturated "-ol" and saturated "-olidine", 6 "-ine", again 7 "-epine", 8 "-osin", 9 "-onin", and 10 is "-esen". On the other hand, the second row, there are rings which does not contain nitrogen. So the rules are different for the rings which does not contain nitrogen. Again, it is divided into unsaturated having double or triple bonds and saturated having no bonds. Again, three-membered, unsaturated, no nitrogen, we'll be using the suffix "-iron". Again, saturated "-iran". Four-membered "-it", and for the unsaturated and for saturated is "-etan", and so on. The nomenclature that I've explained, it can be revised one more time. For example, first is simple heterocyclic rings containing one heteroatom. Now, the first rule is the heteroatom in the ring is counted as 1 and the other atoms are numbered in either clockwise or anti-clockwise. For example, pyridine. Pyridine is a benzene ring containing nitrogen atom. Now, as per the rule, the number 1 is given to the nitrogen and the rest of the carbon atoms, they can be either numbered clockwise or they can be either numbered anti-clockwise. The second rule is if one substituent group is present, then the numbering is given in such a way that the substituent should bear least possible number. For example, in the first structure, there is a ring containing nitrogen atom and on the third position there is carboxylic group. Now, according to the rule, it has to be numbered in such a way that this carboxylic group receives the least number. So, starting first, as per the first rule, one number is given to the nitrogen, and if we go on in the anti-clockwise direction, third number is given to the carboxylic. But if we go on to the clockwise direction, fifth number is given to the COOH, that is the carboxylic group. So as per the rule, the first structure is correct one because in this structure, the carboxylic group or the substituent receives least number, that is third number, as compared to the second structure where it receives 5 number. Third rule, if more than one substituent are present in heterocyclic ring, then they should bear least set of numbers. The groups are arranged in alphabetical order. The correct method of numbering is shown in first structure. Alphabetically, if it is arranged, again, the first number is given to the heteroatom, that is nitrogen, and second will be given to methyl, then OH, CH2OH, and then CH2OH. So, the correct method of numbering is shown in structure A as the substituents bear least set of numbers. Fourth rule, if the heterocyclic ring contains two or more different heteroatoms, what about if there is oxygen or if there is phosphorus in the ring along with nitrogen? Then it is always numbered according to the order of preference. And the order of preference for position 1 is always oxygen, sulfur, then nitrogen. If these three heteroatoms are present, first numbering will be given always to the oxygen, second to the sulfur, and third to the nitrogen. And the other heteroatoms are given lowest possible numbers. The example is oxazole. In this, we have oxygen and nitrogen as two different heteroatoms. So, as per the rule, first number will be given to oxygen and second number or next number will be given to the nitrogen. Similarly, second example, thiazolidine. There is sulfur, there is nitrogen. So, as compared to sulfur and nitrogen, sulfur is given more preference than the nitrogen. Thus, in oxazole, oxygen is numbered 1, and in thiazolidine, sulfur atom is numbered 1. In both these cases, the ring is numbered in anti-clockwise because the second heteroatom bears the least number of possible number. Fifth rule is, if simple heterocyclic ring contains 2 or more nitrogen atoms. What about there are more than one nitrogen atom, means same number of heteroatom? Then the saturated nitrogen, the one with amino group with the hydrogen, should be at number 1. For example, pyrazole. In this the first atom, first nitrogen, it has hydrogen, so it is given the first number. Next is sixth rule. In the case of fused ring compounds, the numbering and the nomenclature becomes more complicated. Trivial names are given to certain fused ring compounds containing heterocyclic ring. Their systemic chemical names are given in different ways. For example, quinoline. This is a very important structure. In this, benzene ring is fused at second and third position of pyridine. Pyridine is a compound that is benzene ring containing a nitrogen. Hence, it is chemically named as 2,3-benzopyridine. 2,3 because benzene is fused at second and third position. The numbering again will start from nitrogen as the first, and it will go to the anti-clockwise direction. But the method of numbering of pyridine rings is different from quinoline. So you can see there are other examples given like azepine. In this, the nitrogen containing ring is placed in centered and 2 benzene rings are placed alongside. So in the following structure, 2 benzene rings are fused at B and F sides. Now what about the B and F sides? The nomenclature, the sides of heterocyclic system or heterocyclic ring, they're labeled as A, B and C, starting from the atom number 1. Thus, quinoline is chemically named as benzo-B-pyridine. B stands for second and third position. Next rule is, in certain fused ring compounds, the numbering is not started from heteroatom. For example, in isoquinoline, nitrogen or the N atom is given 2. In acridine, N atom is given 10. And in phenothiazine, sulfur and nitrogen are given 5 and 10 numbers respectively, as it is shown in the given examples. Nextly, the name of 5-membered heterocyclic ring containing 2 double bonds. If we have 5-membered ring, heterocyclic ring, and it has 2 double bonds, its name always ends with ol. For example, pyrrole, and on the other hand, imidazole. In this type, the terminal E of ol is replaced by L. It's replaced by, in the first structure, it is replaced by ein if one double bond is saturated, and in the second structure, the E is replaced by idin if both bonds are saturated. Means, if we are replacing the bonds with no bonds, then the E of pyrrole will be replaced in the first structure by ein, and the E of imidazole will be replaced by idin, as you can see in the given examples. Next, 6-membered heterocyclic containing 3 double bonds generally ends with ein. For example, pyridine. It is 6-membered ring and it is heterocyclic, so it will generally end with ein. First example, pyridine, and second is pyrimidine. Pyrimidine is having 2 nitrogen atoms, but it is 6-membered ring. Next, the name of heterocyclic ring can be obtained by using prefix for a heteroatom. For example, if we're having nitrogen as a heteroatom, we'll use the prefix as a azo or per. Sulfur, thia or thio, and for oxygen it is always oxa. Thus, thiazole is a 5-membered ring containing 2 double bonds. Since it is ending with ol, that means it is 5-membered and it is having 2 double bonds and 2 heteroatoms, namely thia stands for sulfur and aza stands for nitrogen. So thus thiazole, it can be splitted and it can be drawn into 5-membered ring containing 2 double bonds and 2 heteroatoms, namely sulfur and nitrogen. Thus it can be written as oxazole. Oxazole stands for C. Oxa, it has oxygen, aza, it has nitrogen, and ol means 5-membered ring with 2 double bonds, that is, it is unsaturated. Similarly, thiazole. Oxazole is a 5-membered ring containing 2 double bonds and 2 heteroatoms, namely oxygen and nitrogen. Similarly, the third structure is pyrrole. Pyrrole can also be named as azole because it contains nitrogen and again 5-membered ring and a double bond. Now, to give chemical name to the given structure of a drug, first of all, you have to choose parent skeletal structure and number according to rules. Second, if the substituents are too complicated, then separate numbering should be given to them. The carbon atom of the substituent which is attached to the parent structure should be given 1. Third, first write the names of the substituent prefixed with numbers in alphabetical order. Fourth, finally write name of parent skeletal structure. Important thing to remember, if nitrogen except of heterocycle of a parent structure is substituted, then the name is always written as N substituent if only one substituent. NN if 2 same substituents are present, and N slash comma N slash if 2 different substituents are attached to nitrogen atom. Let's see the example of first drug, that is acetazolamide. The parent structure is 1,3,4-thiadiazole. Now I will explain how 1,3,4-thiadiazole is chosen. Since we can see the parent ring structure, there are first of all 2 different heteroatoms. First one is sulfur and then there are 2 nitrogens. So as per the rule, order of preference is given to sulfur. So sulfur will be always given the first number, and the next is second carbon, and the third one will be the first nitrogen and fourth one will be the second nitrogen. So 1, 3, 4. On the first position we have sulfur. Sulfur stands for thia. Next is 2 nitrogen. Nitrogen stands for aza, but since there are 2 nitrogen, we'll write di. So the parent ring or the parent structure becomes 1, 3, 4 thia diazole. Azole stands for unsaturated, means containing double bond and 5-membered ring. So 1,3,4 thiadiazole is chosen as your parent structure as per the first rule. Second, at second carbon there is 4 acetamido group, and at the fifth carbon sulfomoyl group is present. So these groups are basically given numbers. Second carbon or the number of the substituent on the second carbon is acetamido group, and the name of the group which is substituted at fifth carbon, it is sulfomoyl. The substituents are very simple. Therefore, the chemical name is written as 2 acetamido, 5 sulfomoyl, and then the parent structure, that is 1,3,4 thiadiazole. So this is the basic numbering of any chemical name if you want to give to any structure of a drug. Similarly, we have chlorpromazine. So in this, phenothiazine is chosen as the parent nucleus. The numbering starts from extreme right, first, second, third, fourth, and the sulfur group receives the fifth, and the nitrogen groups receives the 10th position. At second carbon, we have chloro group, the halogen, and at 10th position, there is a complicated substituent. Now for numbering it, you have to number first the complicated substituent. Therefore, the carbon atom attached to N Nitrogen of phenothiazine is numbered as 1. The chemical name of the substituent that is attached is 3-dimethylaminopropyl, which is written in the bracket. Thus, the name of this compound becomes 2-chloro-10 because it is attached at the 10th position, and the name of the number of the constituents becomes 3-dimethylaminopropyl, and the parent group comes at the last. Parent name comes at the last. That is phenothiazine. Similarly, we have the next example of chlorpheniramine, which can be numbered in a same way. Next is to draw chemical structure from given chemical name. Now, first of all, draw the parent structure. Again, we are given with the chemical name, and from that name we will pick the parent structure, parent compound, or the nucleus. Second, you have to give numbering according to the rules. Third, write the groups at specified positions. For example, we have a structure, we have a name 2,4-diamino 5 bracket start 3,4,5 trimethoxybenzyl pyrimidine. It is very clear that pyrimidine is the parent nucleus. Pyrimidine is a benzene ring containing 2 nitrogen groups at first and third position. So first of all, we'll draw the structure of pyrimidine. Second, 2 amino groups, because in the starting we have 2,4-diamino. Diamino means 2 amino groups at which positions? At second and fourth position. So 2 amino groups are present at second and fourth position. We'll draw 2 amino groups at second and fourth position. Third, at fifth position, the substituent, which is very complicated, it is written in bracket, and hence that substituent has given separate numbering. To that substituent will give a separate numbering. That means there is 3,4,5 trimethoxybenzyl, benzene ring with 3-methoxy-methyl group, right? So hence the benzyl group C is substituted at third, fourth, and fifth position by 3-methoxy groups. Similarly, the heterocyclic compounds, for example, pyridine, have many properties similar to the aromatic compounds. Now, the heterocyclic rings compounds with more than one heteroatom. The usual rules for stems to indicate ring size and suffixes for degree of saturation are used, as are the prefixes for the various heteroatoms. They are listed in following order of priorities, derived from the main groups of the periodic system, and then within each group by increasing atomic number. For example, we have discussed earlier, oxygen is given more preference than sulfur, selenium, and tellurium. Next is nitrogen is given more preference than phosphorus and arsenic. But we since have 4 major groups, and we need 4 major order of preference as discussed earlier, that is oxygen, sulfur, nitrogen, and phosphorus. So these are the revised rules that we've already discussed in the previous slides. Each heteroatom is given a number as found in the ring, with that of the highest priority given position 1. A saturated heteroatom with an extra hydrogen attached is given priority over the unsaturated form from the same atom, as in 1H13-diazole. The numbers are grouped together in front of the heteroatom listing, thus 1,3-oxazole, not 1/oxa3/oxazole, that is combined. It is 1,3-oxazole. The heteroatom prefixes follow the numbers in the priority given previously. Rings with more than one heteroatom, since we've discussed it already, punctuation is very important. In the examples to follow, a comma separates the number and a dash separates the numbers from the heteroatom prefixes. A slight modification is used when 2 vowels adjoin, one in deleted as in the listing for oxaza, which becomes simply oxaza. That means the 2A, that means only one A is required, since we have the vowel beginning with the next word beginning with a vowel, that is A. Next is, as for monohetero systems, substituents on the ring are listed alphabetically with the ring atom number for each, not grouped together. Same rules for the bicyclic compounds. System where 2 rings share a common or a single double bond, which are said to be fused rings. Now, a common case is where a benzene ring is fused to a heterocyclic ring. The name begins with the prefix benzo because benzene ring is combined. The point of attachment is indicated by a letter that defines face of the heterocyclic involved. Thus, the 1-2 position on the heterocyclic ring is always A face, 2-3 position is always B face. You will remember this because we have discussed it in quinoline as an example. In quinoline, benzene ring was attached at 2-3 position with the pyridine group. So that's why we have used B word because it stands for attachment at the second and third phase. Next is 3-4 is the phase C and so on. After the name is established, the ring atoms are given new numbers for the entire bicycle. The letters for the faces of the monocycle are placed inside the ring, and the numbers for ring positions of the bicycle taken as a whole are shown on the outside. The final numbering always begins at the position next to the benzo rings and group, and that the heteroatoms are given the lowest number possible numbers, observing the rule oxygen, sulfur, nitrogen, and phosphorus. The position of ring fusion bear the number of preceding ring atom with the letter A attached. Brackets are used around the face letter and the name is put together without spaces, except that a dash separates the bracket from ring numbers if present, as in benzo, D, 1,3-thiazole. A convention frequently followed is to write the structure with the hetero ring on the right and with its heteroatom at the bottom. If two heterocyclic rings are fused, additional rules are required. A parent ring is selected and the other ring is considered fused on, as was observed from benzene fusion. Some rules are follows. If one ring contains nitrogen, it is considered the parent and its name is placed last in the compound's name. Now, the rules that we've already discussed in the previous slides, they can be applicable to these structures. Just you can have a list, you can have the examples of the classification that we have done. For example, 3-membered rings, which are containing only one heteroatom. If the heteroatom is nitrogen and it is saturated, the names become aziridine. If it is unsaturated, it becomes aziridine. Next, oxygen. If it is containing oxygen heteroatom, the name becomes ethylene oxide, and for unsaturated, oxyrene. Sulfur, thiorane, for unsaturated, thiorine. You can apply the previous rules on these compounds. 3-membered rings, but they are having two heteroatoms, oxygen, dioxyrane, nitrogen, diazyrine. 4-membered ring, again containing one heteroatom. If the heteroatom is nitrogen, saturated azotine, unsaturated azide. Oxygen, saturated oxetane, unsaturated oxide. Sulfur, saturated thiatine, and unsaturated thiate. Next is 5-membered ring, again containing one heteroatom. Nitrogen if saturated pyrrolidine, if unsaturated pyrrolene or pyrrole. Oxygen, saturated tetrahydrofuran, and unsaturated dihydrofuran furan. Similarly for the sulfur, phosphorus, silicon, and arsenic. 6-membered ring, again containing one heteroatom, nitrogen, oxygen, sulfur. You can have a look if it is saturated for nitrogen, piperidine, and unsaturated pyridine. If the heteroatom is oxygen, saturated tetrahydropyran, and unsaturated pyrrolium. And similarly for the sulfur. 7-membered nitrogen, azepane for saturated and for unsaturated azepine. Again, oxygen, oxypane for saturated, oxypine for unsaturated, and for sulfur, thiopane for saturated and thiopine for unsaturated. Again, the last one, 8-membered ring containing one heteroatom, nitrogen, azocane for saturated, azocine for unsaturated, oxygen, oxysane, and and sulfur, thiocane. These are some basic organic groups, names of the organic groups that will be very useful in this chapter. For example, the alkyl groups, methyl, it stands for CH3. If there is C2H5 group, stands for ethyl. CH2, CH2, CH3, and propyl. And if it is branched, CH, CH3, CH3, isopropyl, N-butyl, straight line, CH2, 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 CH3, N-butyl. As we know that methyl, methane stands for 1 carbon, ethyl, eth stands for 2, propyl stands for 3, and then butyl stands for 4. Similarly, these are some organic compounds which will be, or groups which will be very useful in this chapter. Second one is aryl. The phenyl ones, no group with benzene, and if there is group with benzene, benzyl. Toluyl, if there is toluene group, CH3. Ortho, it is 1, 2. Meta, it is 1, 3. And para, it is 1, 4 positions. You can have look at these groups. They are very, very important, like amino. NH2 stands for amino. N, if there is NH, separate in CH3, that is methyl amino. If it is NCH3, CH3, dimethyl. If there is NC2H5, C2H5, diethyl amino. Next, there are few other important like guanidine, these bioguanides. These are the substituents which will be used in the drug structures. Carbonyl, oxo, C double bond O. Formyl, CH double bond O. Next is carboxyl groups. If there is C double bond O and OH group, that stands for carboxyl. Acetyl, C double bond O, CH3. Acetoxy, C double bond O, single bond O and CH3. So these are the various groups that can be revised.